Hello everyone, it's Dr. C. What I'd like to do in this video is work through the problems from the spring 2018 exam in the hopes of helping you prepare for the upcoming exam this semester. So one thing I want to point out is, I changed things up a little bit from semester to semester. So there are a couple of problems on this exam that we haven't covered, and those I believe are problems 15 and 16. There's also a couple of things that we have covered that are not on this exam, and I will mention those at the end. Okay, so I covered things in a little bit different order this semester, and so this exam, 90+% applies to what we're doing now, and I'll mention where it falls a little short. All right, so let's get to the first problem. So we didn't quite finish the kinetics chapter before the first exam, and so we were still in the middle of integrated rate laws. How does concentration change with time? Now, as I look at this first question, I notice in my choices it's talking about plotting data, so my initial thought is, I'm thinking about linear equations that have a straight line form. The other thing that I notice is the rate law that's given where the concentration of reactant has an exponent of 1. So that tells me this is a first order reaction. And since I'm looking at plots, straight line plots, I think about the integrated first order rate law that has a linear form, and that is this one. All right, y equals mx plus b. So if we plot y, natural log of the concentration, versus x, time, and it is indeed first order, which we do know that, we will get a straight line. And so certainly A is true. A plot of natural log of the concentration versus time gives a straight line. That's true. What about B? Concentration versus time, does that give us a straight line? No, and only in a specific situation. Zero order, yes. Okay, but in general, concentration versus time is a curve like that. That the reaction starts quickly at first when there's high concentration of reactant and then slows down as reactant is consumed. Again, remember the collision theory of reactions. Molecules must collide to react. And if there's fewer molecules to collide, reaction slows down. And then C, we're going to see that in the second problem, that's actually the plot for a second order reaction. 1 over concentration versus time would be for second order. And let's save that for the next one. So the only correct answer there is choice A. All right, let's go to problem 2. Now, this one is also talking about a plot. So again, my mind is thinking, okay, what are the linear equations? It's concentration versus time. That takes us to integrated rate laws. All right. Now, the other thing that is given in here is information that allows us to get to the rate law. It's zero order with respect to y. All right, so that's important. So here are our two reactants, x and y. So it's essentially telling you y is not in the rate determining step. So our rate law is just going to depend on reactant x. Now, we do need to know what the exponent is, and that's where the plot comes in. A plot of 1 over concentration versus time gives a straight line. And that's what I was mentioning up above. 1 over concentration, and in this case we are using x rather than a, but that's okay. This is the second order integrated rate law that is linear. Y equals mx plus b. So a plot of y versus x, 1 over concentration versus time, if it's second order, we should get a straight line. And in this case, we do get a straight line making that plot, so it tells us this is second order. In this case, with respect to x, because you're told it's zero order with respect to y. Correct answer is choice B. All right, so those are the plots for first order, second order. Those are the most important. There is an integrated rate law equation for zero order. That looks like this. This is zero. Maybe I should write the word zero, because who knows if that's a zero or an O. Right? So there, concentration versus time would give us a straight line. And that's because for zero order, rate is constant. Rate of reaction is constant. All right, cruising right along here. One thing we also looked at in this chapter was radiocarbon dating, or just dating using radioactive decay. It doesn't have to be carbon, but carbon is an easy one to focus on. So carbon-14, radioactive, it decays by beta decay, kicks out electrons that are formed and then emitted from the nucleus. And so we can measure how many beta particles are coming off per time, and it will allow us to date that artifact. Now, you are given decay rate of the skull. Then it talks about a living organism having a different decay rate. Again, that decay rate is proportional to concentration of carbon-14. Higher concentration of carbon-14, higher decay rate. Lower concentration of carbon-14, lower decay rate. And that will allow us to date the object. So the other thing to keep in mind is all radioactive decay follows first order kinetics. So that allows us to use the integrated first order rate law. How does concentration change over time? This is a different version, or a rearranged version of the first order integrated rate law that we saw up above in problem 1. And I think this is the easier one to use when you're solving for time, which is what we're doing here. How old is a skull? We're solving for time. Now, we do know the concentration at the later time. We do know the initial concentration. The other thing, though, we don't know in this equation is the rate constant. So it's very common that we are going to get the rate constant from the half-life. And so plug in the half-life given there, 57.15. Plug that in, solve for K. And I left my calculator across on the other side of my office. Excellent planning on my part. All right, so here we go. So this comes out to be about 1.21 times 10 to the negative fourth. And since half-life was in years, we divided by years. So this is going to have units of 1 over time. All right, now we can plug that in along with the concentrations. And again, they're not concentrations, but they're proportional to concentration. So let me just come down here. So the concentration at the later time is lower. And I'm not going to write the unit because the units will cancel. So 850 and then 15.3. And again, higher concentration, higher decay rate. Lower concentration, lower decay rate. So it is directly proportional. We plug in our rate constant and solve for time. And we should get a time of about 2.39 times 10 to the positive fourth years. And I'm having trouble scrolling back up here to see which one. So I don't know if I rounded or if I rounded when I set up this problem for the exam. I think I rounded this 1.21. If I had kept more digits in my calculator, probably would have gotten 2.38 times 10 to the fourth. All right, so there's using radiocarbon dating to find out the age of a artifact. All right, so that's kind of the last part of kinetics, integrated rate law material. A good part of this exam is going to be on equilibrium. And mostly, in this case, gas phase equilibrium in chapter 15, and then we moved into some acid-base equilibrium in chapter 16. So, place to start, writing the equilibrium constant expression, products over reactants, raised to the power of the coefficients. Pure solids, pure liquids do not enter into the expression. So this one is just going to have SO2 in the numerator, squared, and in the denominator, O2 cubed, and that would lead us to choice E. All right, so don't miss ones like that. All right, there are two definitions of equilibrium that we've used, and make sure you know these. You don't want to miss definition ones on the exam. And choices A and C are definitions of equilibrium. So both of those are correct. So the correct answer to this is choice D. At equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. All right, so that's maybe the definition we've used more often, and I'm pretty sure that is. But what that also implies is choice C, because reactants are going to products at the same rate that products are coming back to reactants, the concentrations of reactants and products are no longer changing with time. Now, it doesn't mean choice B, because, that reactants and products are not changing with time doesn't mean the reaction has stopped. And that's what choice B implies. So equilibrium is dynamic. It's just, in some ways, I like to think of it as circular. Reactants, products circling back again. And there's constant reaction going on. But the forward and the reverse are the same. Concentrations are no longer changing with time. All right, we spent some time talking about the magnitude of K, and that's what we see in problem 6. You need to know what the magnitude of K tells you in terms of how the reaction goes toward completion. Does the equilibrium lie far to the right? Does it lie far to the left? Or does it lie somewhere in between? And the magnitude of K tells you that. Now, the larger the K, so here's 10 to the third, that's a relatively large K, that equilibrium is going to lie toward products, toward the right. Really small K, 10 to the negative fifth, that equilibrium lies to the left, toward reactants. So remember, your general form of the equilibrium constant is products over reactants raised to the power of the coefficients. So a lot of products, large K, large numerator. Conversely, a lot of reactants, large denominator, small k. Make sure you know what the magnitude of K tells you. So we're looking to rank these increasing tendency to go to completion, which means go from reactants to products. So the largest K will go more toward products. The smallest K will stay mostly at reactants, not go very much to products. So the correct order here is 3 is going to be less than 1, because 1 is kind of, excuse me, 1 is still small, but not as small. So this one's going to be still leaning toward the reactant side, but kind of in the middle of those two, obviously. And then reaction 2 will go most to completion. Choice D. All right. Hopefully my voice will recover here. We didn't spend a lot of time on this equation, but we did talk about it a little bit. And I apologize. Let me pause for just a second. All right, so I think I'm back. We'll see how I hold up here. All right, so get this out of the way. We did talk about this equation. It is a way to convert between Kp and Kc if you need to. This one's not asking about a conversion, but when do they actually equal to each other? And there is a case where they will equal. It's when delta N, which is change in moles of gas only, product, moles, minus reactant, final minus initial. Okay, so take moles of gas product, subtract moles of gas reactant. If that comes out to 0, then 0.0821 t to the 0th power, that's just going to be 1, and we will end up with Kp equals to Kc. So let's look and see if we can find one where the moles of gas do not change in going from reactant to product. And it looks like we're looking at choice E here. 2 moles of gas reactant, 2 moles of gas product. Don't worry about the solid. That's not going to contribute to the pressure inside that system. And it looks like all the other ones, the moles of gas do indeed change. Okay, so the only one that would have Kp equal to Kc would be choice E. All right, another thing we did early in the equilibrium chapter was look at how the equilibrium constant changes if we manipulate the reaction. All right, so what if we reverse the reaction? What if we multiply it by a factor? Okay, probably seems like we did this quite a long time ago. All right, but it really wasn't that long ago. So what we do is compare these two reactions, and we notice that the reaction is reversed. What was a reactant in the first reaction is now a product, and what were products are now reactants. So what happens to the equilibrium constant when we reverse the direction? Yeah, it's 1 over. So this new equilibrium constant, let's call it K prime, it's going to be 1 over the initial. All right. Now, what else was changed here? Yeah, we multiplied the equation by 4. Now be careful here, because we raised the power of the coefficients, we don't multiply the original equilibrium constant, we raise it to that power. Okay, so remember the general form of the equilibrium constant. Products raised to the power of the coefficient over reactants raised to the power of the coefficient. So we're going to have to do the same thing there, raised to the 4th power, since we multiplied the equation by 4. So in this case, we have to invert or take the reciprocal, and we have to raise it to the 4th power. .27 times 10 to the 10th. We only had 2 sig figs, so to 2 sig figs, 4.3 times 10 to the 10th. All right, so make sure you know how the equilibrium constant changes when manipulating a reaction. Now, we're actually getting into some real calculations with equilibrium. All right, now be careful, read the problem carefully. And as you read this, the first thing that jumps out at me is it's telling you you are at equilibrium. So these are equilibrium amounts. 1 mole of H2S, 4 moles of hydrogen, 0.8 moles of sulfur. That means you do not need an ice table. No ice table needed. So we do know that our Kc expression, products, hydrogen, raised to the power of the coefficient, 2, sulfur, power of the coefficient, 1, and then hydrogen sulfide H2S, power of the coefficient squared. Now be careful, Kc, these square brackets, what we have to plug in there is molarity. You have moles. Now, There was one sapling problem, I believe, where when they solved it, they plugged in moles. You can do that only if the moles of products equal the moles of reactants. All right. So generally, don't even worry about using moles for equilibrium at this point. Always just think Kc is molarity, Kp is pressure in atmospheres. So in this case, we have to convert these. We do have a 4-liter vessel. So hydrogen, 4 moles divided by 4 liters is going to be 1 molar. Sulfur, 0.8 divided by 4, 0.2. And then H2S, 1 mole divided by 4, it's going to be 0.25 molar. And that is squared. So you should come up with a Kc value of about 3.2. Choice C. All right, so again, read carefully. If you're already at equilibrium, don't make it harder than it is. And if you set up an ice table, you won't get the right answer. You already have the equilibrium amounts to plug directly in to the expression. All right, another thing that we did in this chapter was figure out, sorry, I lost my train of thought there for a second, happens a lot, figure out what happens if we're unsure which way the system's going to shift to reach equilibrium. Now, a lot of the problems we worked, one side of the equation, there was zero, whether it was zero product or zero reactant. So we knew which way it was going to shift. But in this case, we have concentrations of all species in that reaction. So it's unclear which way this system will shift to reach equilibrium. And that's where we have to calculate the reaction quotient. Now, the nice thing here is the setup looks just like K, the equilibrium constant. But we are plugging in the initial concentrations. Most likely Q will not equal to K, and that will tell us which way this system is going to shift to reach equilibrium. So plugging in the values, we were given molarity directly, so we can just plug those in. Hydrogen iodide was 3 molar. Hydrogen is 0.25 molar. And iodine is 0.5 molar. Come up with 72. All right, now, that number by itself doesn't tell us which way it's going to shift. We have to compare that to the equilibrium constant. So in this case, Q is greater than K. So first off, we are not at equilibrium. Absolutely not. At equilibrium, this value, which is 72 now, will have to equal to 45.9. So Q is too large. How do we make Q smaller? And again, note, just like K, products over reactants raised to the power of the coefficients. So if Q is too large, our numerator is too big, or our denominator is too small, or in this case, both. All right. So we need to get rid of products and make reactants. So the system is going to shift left. All right, so the system is not at equilibrium. E is out from the beginning. Q would have to equal to K for that to be the case. So we're not at equilibrium. Q is greater than K, so it's either B or D, but it's not, and it's actually D in this case because right to left, products to reactants, or products to reactants. It's not going to go from left to right, reactants to products. Okay? There you go. Compare Q to K, figure out which way we are going to shift. All right, so now I see, as I look at my choices, looking at my choices here, I see the equilibrium constant in terms of X. So right away, I'm thinking ice table. So let's see why we need an ice table for this one. 2 moles of SO3 in a 1 liter container. That's our product. It's only saying we start with product. So we can't be at equilibrium. So we're going to have to set up an ice table. So initial in terms of molarity. 2 moles, 1 liter, 2 molar. No reactant to start. All right. This one, it's clear cut which way it has to go. At equilibrium, we're going to have both reactant and product. All right. Now again, remember, some equilibrium will lie far to the left and we'll end up with mostly reactant. Some equilibrium will lie far to the right and we'll end up with mostly product. But we're going to have some of each. So we can't have 0. So this reaction has to shift. Product is going to have to produce reactant in this case. Watch your coefficients. You're going to see them in the x term, and you're also going to see them in the exponent. So for this equilibrium, products, SO3 squared, so there's your coefficient again. SO2 squared, another coefficient, and O2. That has a coefficient as well, but it's 1. So now we plug in. Product is 2 minus 2x, quantity squared. Reactant is 2x squared times x. And let's see which one that is. Looks like choice A, if I'm looking at that correctly. Okay, so this problem was just testing, do you know how to set up an ice table? Don't even have to solve here, but make sure you can set up an ice table. You have to do that correct first before you could solve for x. So be careful. If you set up your ice table incorrectly, you're not going to solve for x correctly. All right. Last part of chapter 15, the equilibrium chapter that focused mostly on just what is equilibrium, how do we solve problems, that kind of thing, focusing mostly on gas phase reactions. The last thing was Le Chatelier, okay? And again, that principle tells us we have a system at equilibrium, we then apply some stress, some change to that system. The system is going to, in a lot of cases, shift to partially offset that stress. All right, so let's look at the first one. One change we could make is a temperature change. Now it's important that you go back to where we started the semester, and we even covered this last semester in Chem 151. What does the enthalpy change sign tell you? And this is a positive sign, so is that exo or endo? Yeah, this is endo, endothermic. What does that mean? We have to add heat to this reaction. This reaction absorbs heat. So think of heat for endothermic as a reactant. We have to add heat to that reaction. All right. So now we are decreasing the temperature. We are, in effect, removing thermal energy from that system. So Le Chatelier tells us it's going to shift to partially offset that change. So the change was removing heat, removing thermal energy. The system is going to shift to replace it. So this system is going to shift to the left to reach equilibrium. Now, what about D? Generally, the equilibrium constant is a constant, but it's only a constant for that reaction at a given temperature. If you change the temperature, the equilibrium constant changes. So in this case, if it shifts left, and I can spell, product over reactant, okay? So if it shifts left, product is going to decrease, reactant is going to increase. What's going to happen to my equilibrium constant? Smaller numerator, larger denominator, my equilibrium constant will decrease. Okay, it doesn't increase, so that's out. So the only correct answer here is choice C. All right, one last thing with this problem. Endothermic reactions, because the system does need to absorb heat, are favored as we raise the temperature. Endo, favored as temp is increased. Okay, now what do we mean by favored? This is endothermic. Favoring would mean going in the forward direction. You can think of spontaneous or pushing that reaction in the forward direction. So increasing the temperature for endothermic is going to shift it to the right, toward product. Doing the opposite, endothermic reactions need heat. You pull energy out of that system, that's not going to favor that endothermic reaction, and it's going to shift back to reactant. I don't know if that helps think about this a little bit differently than we just did. All right, 13. Now we're going to change the volume of the container. Which of these will shift toward products to the right? All right, so let's look at what change we made here. Increase volume. What does that do to pressure? Yeah, they're inversely proportional. That will decrease the pressure, so the system is going to offset that. So it's going to shift to increase the pressure back up. Well, how is it going to do that? Yeah, it can increase pressure by making more gas, more moles of gas, more gas particles, because pressure of a gas is directly proportional to moles of gas. All right, so which of these shift to the right? Well, the ones that shift to the right are ones that have more moles of gas on the product side. So choice A, we have a total of 3 moles on the product side, only 2 on the reactant side. So that one will certainly shift right. B will not. We only have 2 moles on the product side, but 3 on the reactant side. That one will actually shift left to more moles of gas. It looks like choice C will as well. It looks like I think I remember I had an error in this problem. I think I have 2 correct answers here, because choice C will also shift to the right. And choice D has the same, so this won't shift either direction. So I remember this problem. I think on the exam was identified, and I told students to put either correct answer. So this one, unfortunately, sometimes I do make mistakes on exams. Try not to. This has 2 correct answers, A or C. Because both of those, when it shifts to the right, we produce more moles of gas, more gas particles, pressure will go up. All right, sorry about that. Bringing back some bad memories. All right, and I think the last one for this part of the recording that I'm going to do today, or at this time of this day, is 14. And this one, we actually do have to solve an ice table. And let's see why. Initially, the concentration of NO2 is 0.05. So it's telling us we're just starting with NO2. We're not starting with N2O4. So right away, you know you're not at equilibrium. We do need to set up an ice table. Initially, my eye is not quite in the right place, but you get the idea. Initially, this is 0.05 molar. No reactant. This has to go left. We have to produce some reactant. So product has to decrease. Reactant has to increase. Again, watch your coefficients. And here are our equilibrium amounts in terms of X. All right, I'm going to need just a little bit more room for this one. Our Kc expression, products over reactants, raise the power of the coefficients. We plug in 0.05 minus 2x squared. Don't forget, you see the coefficient twice, 2x, and that squared term over x. Now, I've worked a lot of these problems. I probably should have read this one a little bit more carefully, but for me, I set up all my ice tables the same regardless of whether I'm solving for X or solving for K. So once I knew that I wasn't at equilibrium, that I was just starting with the product in this case, I immediately just jumped into my ice table in terms of X and plugged it in. Now as I read further, I'm giving an equilibrium concentration of NO2, and I'm asked to solve for Kc. So now that I read the question more carefully, if I'm solving for Kc, X must be given. Now, sometimes it's given directly, and I could have made this problem easier by giving the equilibrium concentration of N2O4, because that one in our table is X. But I did not do that in this problem. And students didn't like this one very much, as I remember from last semester, because I gave the equilibrium concentration of NO2, which in our table is 0.05 minus 2x. Don't let that bother you. All it does is it makes us do just a little bit more work, because we're saying the equilibrium amount of NO2 is 0.05 minus 2x. Well, you're told that it's actually 0.02. So 0.05 minus 2x is equal to that 0.02. Now we just have to solve. 2x is equal to 0.03. Do a little algebra here. And it looks like our x is equal to 0.015. Now we can plug in. So our denominator is x, 0.015. We could plug our x back in up here, 0.015 for our x, but we were given the equilibrium concentration of NO2, so we might as well just plug that in, because when I take 0.05 minus 2x, I'm going to get 0.02. Now it is still squared, and so our Kc value in this case is 0.0267, which is choice E. All right. That takes us through the general equilibrium chapter, let's call it that, where we defined equilibrium, we learned how to write equilibrium constant expressions, we learned how the equilibrium constant changes when we change direction, we learned how to plug into the equilibrium constant expression. We learned how to set up ice tables. We learned Le Chatelier's principle, all of that good stuff. All right. That's the end of that material on this exam from last year. Now, disregard 15 and 16 on this exam. We will do that later in the semester. Turns out, and you will not remember this, but when we started the semester, we started with thermo, and one thing we covered was delta G, the free energy change. And we skipped a section that related the free energy change with equilibrium because we hadn't covered equilibrium yet. Now, sometimes I will cover this material right after I finish the general equilibrium chapter. Sometimes I cover it a little bit later in the semester. We're actually going to cover that a little bit later this semester. All right? So disregard 15 and 16. When I post part 2 of the recording, now this is where acids and bases start. And this is chapter 16 in the sapling book that we're using. All right, so this material going forward is all relevant to what we're doing. Okay, so anyway, I will post this first part and I will post the second part later this week. All right, talk to you soon.